ยากรท่านต่อไปนะคะจะมาบรรยายในหัวข้อการออกแบบคอยสำหรับเครื่องปรับอากาศที่ใช้เทคโนโลยี Microgroove ค่ะโดยวิทยากรท่านนี้ค่ะได้รับปริญญาเอกจากมหาลัย2 สถาบันนะคะคือมหาลัยอิลลินอยส์และซ่างไห่เจียวทงค่ะท่านมีประสบการณ์กว่า10 ปีในการดีไซน์เครื่องปรับอากาศและระบบของ Heat Exchanger ค่ะขอเรียนเชิญดร. Tao Ren ค่ะ
Good morning, everyone. I'm very happy to stay here to share my experience on the Microgroove heat exchangers design for RACs. First, let me introduce myself. I'm from Shanghai Jiao University from China, and we have cooperated with ICE for developing small diameter tube for more than 10 years. We have cooperated with almost of the air conditioner manufacturers in China, including GLI, Media, Hisense Cologne, TCE, and so on. We have a lot of experience on the developing the small diameter tubes, tube fin dies, and fin patterns, and the design the flow circuitry and the system for the air conditioners. Here is my presentation's content. Number one, I will introduce advantage and application of small diameter tubes. As we all know that the Kerry has introduced the defining the small diameter copper tube heat exchanger is we say the diameter of the copper tube is less than 5 millimeters. And we know that the copper cost will reduce 20 to 40% when we switch from the 9 millimeter or 7 millimeter tube to 5 millimeter tube. Of course, the pressure drop will be high. Another advantage is the cost of the refrigerant. The cost of refrigerant will reduce 30 to 40%. When we switch to 9 millimeter or 7 millimeter to 5 millimeters, and more importantly, the 5 millimeter is more compact. The whole volume will be reduced when we designing high efficiency heat exchangers. For example, like 5-star heat exchanger, 5-star air conditioner, or the level 1 air conditioners in China. 5 millimeter has plays an important role, to get high efficiency. And to my experience, that in some cases, when we want to get very high efficiency, and our volume is very limited, especially for the indoor unit, and 5 millimeters performance is much better, much better than the 7 millimeter or the 9.5 millimeters. So in China, of course, in Japan, you can buy such kinds of machines that the energy efficiency is very high, and they use 5 millimeter for the indoor unit, and they don't use 7 millimeters. So that's the advantages of the 5 millimeter, more compact when we do high efficiency heat exchangers. Currently now, the 5 millimeters heat exchanger now in China, we already applied in the split one, commercial one, the split AC, or the like a window machine cabinet. We also applied the some Coca-Cola cabinet with 5 millimeters, and it was succeed, and it's much better than it's much better than the 7 millimeter or 9.5 millimeters, and the cost is much lower. So here I will introduce the two key technologies. One is develops small diameter fins. Second is how to make the system matching when we use the 5 millimeters. For the designing of the 5 millimeter fins, and we will know that for the early 9.5 millimeters, we designed the fin like 25.4 multiply 22. This is the most widely used fin tool pitch for the 9.5 millimeters. And in 7 millimeters, we have some changes. We make 21 multiply 12.7, and we also have the 21 multiply 18.2. And some manufacturers get 21 multiply the 21 multiply 22. Very wide fin. And so it's a question that what is 5 millimeters fin? What is the fin pitch? Which one is more efficiency? Because currently, if you focus on the 5 millimeters fin patterns in China, there's tons of the fin patterns, more than 10. A lot of. So which one is better and which one is more high efficiency? I think everybody is asking these questions. Normally the fin. Is it work? Okay. Normally for a fin the temperature. This is a color of the tube, and as a distance far away from the color of the tube, the temperature will also goes down. So we design our. If we want to, our fin is more efficiency. We hope our fin, the PT is this distance, and the PL is this distance from here to here. And we want, the ideal is that the PT divided the PL is 1.15. It's a triangle. It's the same distance triangle in English, say. And we hope our efficiency is like here. But at first, when we, most of the fin is copied from Japan, and the Japanese guys did fin like this. This is not the fin. This fin is not good. This fin is still good. It's very good fin, but they have their used case. Their case. In their case, it's perfect. But for some Chinese manufacturers, and they use their fin, this kind of fin in their case, and found that it's not good, and they complain that why is fin like this? It's terrible. So we found that for our traditional use, not Japanese guys use case, for our traditional use, we found that the fin efficiency is lower, so we need to modify that. And we hope that our ideal is that the PT divided PL is 1.145. In this case, we can find that the fin efficiency is the highest one, and we calculate the theoretically. So in this case, the air temperature around the surface, air temperature surface is constant. So that we can have the analytical solution, and we can prove that the triangle, the PT divided PL is equal to 1.154 is perfect. But in the real heat exchanger, as the wind goes through the fins, the temperature will goes down or goes up. For the indoor unit, it goes down. For the outdoor unit, it goes up. So things changes. So we also make a CFD analysis. As the temperature is changed with the airflow, we found that the best fin efficiency is close to PT divided PL is close to 1.2. It's quite close to 1.145. 1.154. So we recommend that when we use 5 millimeters, just for the traditional use, we use 1.154 for helix changer. But when we go further to investigate that, yes, you have a high efficiency fin, but as we all know that copper price is much higher than the aluminum. So, and the copper density is is much higher. It's almost three times of the aluminum. So in this case, we have a compromise. Maybe our finish efficiency is not very perfect, but we want to get the lowest cost, and we get the best performance. That's why it's push us to go further investigation. So we only want to get the best performance and pay the lowest cost. So what kinds of thing is good? In this case, we push us to thinking about this question, and so we see now our situation is we want to max our UA, and we want to spend the lowest C cost, and we want our pressure drop, our fin, our 5 millimeter is larger than the 7 millimeter. So this is the case we push us to think about more about the fin designs. So we see here is we divided one fin is based on the fin efficiency. It's 18 multiplied 15, and this is we have get the marks of this. As I talked before, this is only considered that UA divided by C, but it's not the C is the lowest. When we want more aluminum, less copper, we get more efficiency heat exchanger, we get lower cost. So we push when we finish this design. So we did another one is that we keep the C. We calculate the C by these equations. Okay, there is the price, the per unit price of the fin of the copper and of the aluminum. We can get from the local price of each market, and we can derive these equations like this one. Say this is PT and PR, and PT and PR combines C. As we PT decrease and the C increase, and the PR increase and C also increase. So in this case, which one? What kinds of the combinations of PT and PR is good? Is perfect. And here we made some calculations. We found a very interesting result. As the cost, increase. As the cost increase, we found a different PT divided PR. The best one for our fin. We calculated a lot of cases, and we get a correlation for that. And we found that as our cost increase, we hope that our fin PR is larger. And when our cost is low, we want to spend less. Our PR is small, and our PT is large. So this is another compilation. You want to increase situations. You want to increase the capacity of the heat exchanger. You want to decrease your cost. And if you want to invest less, use a larger PT and a small PR. If you want to get a higher efficiency, you want to invest more, get a more efficient, high efficiency heat exchanger, more high efficiency air conditioner. Now, decrease your PT and also increase your PR, and you will get more efficiency. This is why it happens in Chinese market. We can find that some 7 minimum tube heat exchanger, their PR is even larger than their PT. That's why they want to get much higher efficiency, and they want to invest more. So it's good to invest more PL because we invest more aluminum, less copper. This is correlations. We get our correlation of about the cost and the PT. We can see that when we want to invest less, PT is large. It's even go to the 23, and then gradually goes down. This is a lot of some things already in the market, and we evaluated. It's more close on this line. So what kinds of the thing is more suitable for your case is just depends on what kinds of the energy efficiency air conditioner you want, and in that case you can get the lowest cost. This is what we did for the slit on the thin surface. As we go to when we move to 5 millimeters, the 5 millimeters, the copper diameter is relatively small compared to the PL. For the 7 minimum or 9 minimum, the diameter is large, so you do not have the heat conduction problem because the diameter is large. But when we go to the 5, you can see that the 5 is relatively small and PL is large. And if you want to transfer the heat from here to these areas, if you have slit, it will become very difficult. So when we move to 5, we need to think about how to avoid this problem. And we did some try-ins, and we found that if we put not the equal distance of the slit on the thin surface, and we get like this, then the heat will gradually goes down here, goes down. So the slit will not break the heat conduction road. So we can get a more higher efficiency thing. And from this safety analysis, we found that if you put the right slit on the thin surface, you can get the heat capacity increased by 5%. It's good. And you need to do nothing, just change the slit. So your cost is the same, just change the slit, you get a higher capacity. This is our test lamp. We have a test lamp to test the fin tube heat exchangers, and to test especially from the air side, we can test the dry working conditions and wet working conditions. And they have this components include 3 loops: airflow loop and water loop and the air acquisition system. This is in our lamp, and this is our facilities. This is our logo, and this is the thermomost test part is here, and we put our heat exchanger here. We test a lot of 5 minimum samples, and we get a correlation. This is our samples. Actually, we get a lot of samples from different companies in China, Green, Media, and Hisense Cologne, Tigo, and so on. And we made a lot of samples, different pitch, and different tube PT and different PL, and 1 row, 2 row, and we get some correlations to predict the 5 meters thin heat exchangers. So because we test a lot, this correlations covers the PT from the 18 to 19, and the PLs from 11 to 14.7. This is the roadmap. When we have the thing, what kinds of thing we have, no matter where we get it, but we have, now we have. Now we want to replace 5 millimeters, replace the 7 millimeter or 9.5 millimeters to 5 millimeters, and then, so how to do it? Is our question. First, we we're trying to directly replace, and we will find that the pressure drop is relatively high, and system EER will be goes down. In some cases, for the outdoor unit, we can directly replace it, and nothing will happen, especially for the cooling only unit. And if we go to the heat pump or go to the indoor unit, and the pressure drop it goes much higher than the 7 minimum, and the EER will goes down. So in this case, how to deal with it? And we did to optimize the heat exchanger. We want to make a compromise of the pressure drop and the capacity. And this is our roadmap. Number one, we get the air velocity profile through the heat exchanger by the CFD or by the experimental test, no matter how you get it. And second, we use this velocity as our input to do the heat exchanger design in our software. Our software can input those velocities because I have samples later, because for some units, especially indoor units, the airflow profile is has a very big significant impact on our flow structure design. And then we do the heat exchanger design. And third, we did the system matching of the cooling model and heating model in RCCM. It's another software. It's for the it's just to test the system performance. In most of the cases, when we design a good heat exchanger and a compatible heat exchanger for the HXM, and we switch it in the system, and we can do directly did experiment. We use system software to calculate it. Both is okay, and the experimental adjustment. And this is an example we did the indoor unit. The original is our 7 minimum heat exchanger. It has two rows. It has 2 rows and 2 parts. And now we switch to the 5 minimum. As you see that this the flow structure is just from 2 to 3, and everything keeps the same. And we can find that the capacity, cooling capacity, and the heating capacity is almost the same as the original one. This is another case. In this case, it's more complicated because the indoor unit is flow, airflow profile is quite different from locations to locations. So before we designing it, we use safety to simulate the air velocity through each tube, and we get this map, like this one. And after that, we use the air profile as the input to the HXM, our software, and we get the flow structure is almost the same trend as the air velocities. So we make a new design. We want to that for each floor, each part of the heat exchanger, they have almost the same vaporization point. In this point, all the refrigerant in the evaporators are evaporized as a gas to gas, and we want to this point the same for each floor. So when we designing this, you be careful. Some larger airflow region, we should get lower or shorter length of the parts of the tube, and some small air velocities profile regions, we should get longer and more longer tubes. And this is what we get. And this is the experimental result. We get very good experimental result as the original one for the indoor unit, almost the same as the original one. This is another case we did for the also it's for the indoor unit. As this is air. Also, at first we try to simulate the airflow rate distributions, and we get these curves, and we put these curves into our software, and we calculated the this is original 7 minimum plus 9 minimum, 7 minimum indoor unit and 9 minimum outdoor unit, and our new one is 5.5, and we almost get almost the same, a little bit lower efficiency, but acceptable because it's within the area of the experiment. And we'll get almost the same capacity, a little bit larger, almost the same, no big difference. This is a simulation result. We can see that for this case, as the flow parts increase to 5, it's more harder or more harder. It's harder to deal with circuitries because it's very hard for us to make the vaporization point at the same point or at the same relative length in the heat exchanger, because the heat exchanger, the total heat exchanger parts has become more complicated, and it's harder to deal with this issue. But for the small case, like 3,300 traditional 2,600 kilowatt and 3,500 kilowatt, it's 1 HP and 1.5 HP is more easier, and for this case it's harder. This is another case. It's for the commercial used outdoor unit. We are trying to make the 5 minimum to replace the 7 minimum heat exchanger. This heat exchanger is a little bit larger than the previous ones. This has 3 rows, 42 columns, and 3 in, 30 in, 30 in, 30 out. Very lot of the branches, and our prototype ODU, this is also the this is a prototype ODU is also 5 millimeters. This is 3 rows, 42 columns, and 3 in, 30 in, 30 out, and this is a fin. The fin pattern is 19.05 multiplied 11.4, and the originally one is 7 millimeter. And at first we use this fin pattern to modify it and get this result. And we found that in some high ambient temperatures, like T3 working conditions, this machine works. This traditional one, this one works not very good. And we suggest them to use a wider fin, more wider fin. And this is the result. That as we extend our fin, our cooling capacity increased 9.5%, and our energy efficiency increased 11.9%. And more importantly, our discharge pressure decreased 60%, 60 kilopascal. So for some T3 conditions, especially the Middle East, India or Thailand, the very hot temperatures region, and the wider fin for the outdoor unit is very useful, very useful. Okay, let's make some conclusions. Heat exchanger with a small diameter tube has the advantages of no cost, no refrigerant, and more compact. And secondly, small diameter tubes are applied on hooked machine, working window machine, and carbonated machine, split type. Fin geometries and flow parts should be adjusted when small diameter tubes are applied in the AC, especially when we are applied in the heat pump for the outdoor unit, and when for the cooling only for the indoor unit, the flow parts should be changed, should be adjusted. We need more refrigerant paths. And with the corporate of our software HXM, the RSSM, of course our RSSM can replace by your experiment, and the air conditioner with better performance can be designed. Thank you.